Okay, so hello everyone. Thank you for attending this master's seminar, both for those of you in person and also for those of you virtually over Zoom. My name is Luke Rowe, and I will be presenting my master's thesis work titled FJMP, Factorized Joint Multi-Agent Motion Prediction. So as autonomous vehicles, or AVs, are beginning to be integrated onto public roads, it's crucially important that AVs safely and reasonably interact with other human road users. And this includes human drivers, pedestrians, and cyclists, just to name a few. And part of what makes driving so challenging for robots, and for humans sometimes, is that we have to interact with other agents, sometimes without being able to directly observe the intent of other agents, while negotiating over a shared road space. So let's take this image as an example, and let's focus on the red and blue agents here. So here we have a congested highway merge scenario where the red agent is trying to merge onto this congested highway. And this is a very common type of interaction seen in driving. And let's suppose for a second that we are the driver of the blue vehicle. So what would we do as the driver of the blue vehicle? So I expect that most of you would anticipate or predict that the red vehicle intends to merge onto the highway in front of the space of this blue vehicle here. And so based on this prediction, you may decide to slightly decelerate to give the red vehicle enough space to safely perform the maneuver. So let's see what happens in reality, how this scenario unfolds. So I'll just play this scenario one more time so those virtually can see it. So what we can see is that what happened in reality lines up with our expectation. So the blue vehicle slightly decelerated to give this merging vehicle enough space to safely perform this maneuver. And part of the reason why humans can perform these complex maneuvers in congested traffic is because we have this model of the behavior of other road users, which we use all the time when we're driving. And I would argue that for autonomous vehicles to safely and reasonably interact with other human road users, they also should have some model of the behavior of other human road users. And this task of learning this model of the behavior of other human road users is exactly the task of motion prediction, which is what I study in this thesis. Okay, so now that I have motivated the motion prediction problem, I'm now going to give a formal definition of the motion prediction problem. So typically the setup is that you're given a data set of scenes where I indexes the scene, and each scene contains three elements, xi, ci, and yi. And we have additional quantities here. We have ni, which is the number of agents in scene I. T observed and T future are the observed windows and the future prediction horizon, which is typically dataset specific. So for motion prediction, we typically care about predicting trajectories over a short term. So T future is usually set to something between 3 to 8 seconds, with T observed usually being between 1 to 5 seconds. And we have three quantities per scene. So we have xi, which is the set of observed states for all the agents in scene I that we wish to predict. And a state is typically represented as the position, velocity, and heading of an agent at a particular time step, as well as other attributes such as the vehicle type and the vehicle shape. CI here is a representation of the high definition or HD map structure. So this could include some representation of the lane boundaries, the center lines, and the crosswalks. And yi is the set of future states for all the agents in scene I that we wish to predict. And this motion prediction problem is set up as follows. So for each scene, you're given xi and ci, so you're given the past states and the HD map representation. And what you want to predict is the ground truth future states yi. And the underlying assumption here is that the past is predictive of the future. But given a past, there's many possible ways that the future could unroll. So typically a motion predictor will not just predict one future, but it will predict k futures, where k is typically set to something like 6, with the requirement that this set of predicted futures are both diverse and plausible. And in practice, we would like that at least one of the predicted futures from this set aligns closely with the ground truth future, which is what happened in reality. So that's motion prediction. So now I am going to set up, I'm going to distinguish the two variants of motion prediction, which are extensively studied in the literature. And this is marginal prediction and joint prediction. So marginal prediction, which is shown on the left here, is the task of predicting the per agent or marginal distribution of trajectories independently for each agent. And it's called marginal prediction because you're learning this marginal or per agent distribution. So for example, a marginal predictor may output that the blue agent has a 50% probability of turning left and following this red trajectory, and a 50% probability of going straight and following this yellow trajectory. And most existing works in the motion prediction literature focus on this marginal prediction problem. And despite the tremendous progress that's made on marginal prediction, it has a gaping limitation, which is that the predictions output by a marginal predictor are not associated across multiple agents. And so a marginal predictor cannot reason about the scene consistency of predictions across multiple agents. So, for example, a marginal predictor would not be able to reason that if this blue vehicle were to follow the yellow trajectory and go straight, and if this green vehicle were to follow this turn left gray trajectory, then this would actually be seen inconsistent behavior because it would lead to a collision. And so for this reason, a lot of recent work has started to focus instead on this joint prediction problem. And instead of learning the distribution at the agent level, you're now going to learn the distribution at the scene level. So for example, a joint predictor may output that the red scene here has 40% probability, where the red scene is such that the blue vehicle turns left and the green vehicle turns left. And this other scene level prediction has 60% probability where both vehicles go straight. And to facilitate joint prediction accurately, you need to be able to reason about the multi-agent interactions in the future. And so we're going to study the joint prediction problem on the right in this thesis. Okay, so now that we have motivated this joint motion prediction problem, I'm now going to state the main contribution of this thesis. And that is that we propose a joint motion prediction framework called FJMP, which factorizes joint prediction into a sequence of marginal and conditional predictions according to the partial order or topological order of a learned directed acyclic interaction graph. So that's a bit of a mouthful, so I'm going to go through the steps of how FJMP performs its prediction here. So this is our input. We're given the HD map structure and the sequence of observed states for all agents. And what FJMP predicts is this directed acyclic interaction graph, like this. And then with this prediction, we are going to predict associated marginal predictions for the source nodes. So that would be agents 1 and 2. And then we are going to predict a conditional prediction for the child node, and that would be agent 0 here. where the conditional prediction is conditioning on the predicted future of its parents in the DAG. So this would be conditioning on the futures of 1 and 2. And so more generally, let's suppose that we have a directed acyclic interaction graph that looks like this. So this means that we have 6 agents in our scene, and the edges represent the interactions happening in the future. So for example, an edge from 1 to 2 indicates that in the future interaction, 1 is influencing 2. And no edge between 2 to 4 means that in the future, 2 and 4 are not interacting. And so here, FJMP would first produce associated marginal predictions for all source nodes. And then we would step through the topological ordering, grab the next set of agents, and do a conditional prediction where we condition on the predicted future of their parents. And then we iteratively continue this process until all agents have a prediction. And then we can aggregate the predictions of all agents, and this is a factorized joint prediction. Another way to see factorized joint prediction is to interpret it as a factorization of the joint future trajectory distribution, which is shown by this equation here. And this factorization is induced by the directed acyclic interaction graph, which we denote by G here. And this is exactly how you would factorize in a Bayesian network, for example. So why should we factorize joint prediction? Why is this a good thing to do for joint motion prediction? Well, the idea for factorization really came about when we identified a limitation with existing joint predictors. And the limitation is that existing joint predictors predict the joint future for all agents in the scene simultaneously. Well, why is this problematic? So let's look at this scenario that we visited earlier, where we have the red vehicle trying to merge onto the highway, and it's interacting with this blue vehicle here. So let's say we wanted to predict the joint future of the blue and red vehicles. Well, existing joint predictors would just predict the future for both agents simultaneously. But remember that the future of blue is really conditional on our prediction of where red is going to go. This is exactly how we were acting as the driver of blue. And so we only really decide to yield because we predict that red is going to merge in front of us. And so simultaneously predicting all the futures does not allow us to model this dependence on the behavior of interacting agents. But factorization enables exactly this. So with factorization, we can predict that red is going to influence blue in their future interaction. And so when predicting blue, we are going to condition on the predicted future of red. This is how FJMP will work. And hopefully this process will lead to more accurate and scene-consistent joint predictions, especially on the interactive scenarios. And so really what this proposed factorization is it's just an inductive bias for the network that encourages accounting for the predicted future of the agents that influence agent N when predicting the future of agent N. So here is a high-level system diagram of FJMP. So we'll go through each component in more detail. Starting with the feature encoder. So any motion predictor is going to need to encode features from the HD map and agent histories to get some agent features that we can use to do trajectory decoding, and in our case, also to predict the interaction graph. And so to do this, we use what's called a lane GCN feature encoder. So lane GCN is a popular open source motion predictor that we use because of its competitive performance and its low latency. And the lane GCN feature encoder is expanded at the bottom here, where as input, we have the HD map and the sequence of observed states, or the agent histories. And the agent histories are fed into a gated recurrent unit. And the HD map is going to be represented in what's called a lane graph, shown here. And so the nodes on this lane graph are going to be positions that are sampled on the center lines of the lane structure. And the connectivity of the lane graph is defined by the left and right neighbor relationships of the lanes, and also the predecessor and successor relationships. And then we can perform a sequence of attention blocks to fuse all this information. So we first perform map-to-map attention over the lane graph, then map to agent attention. This is going to fuse the information about the lane structure into the agent embeddings encoded by the GRU. And then finally, agent-to-agent attention is going to learn some interaction patterns in the agent histories. And then finally, what we're going to get is a set of lane GCN encoded features for each agent, shown here. And these are color coordinated and correspond to the agents here. So that's the feature encoder. So next, what FJMP does is it has what's called a proposal decoder. And this proposal decoder is an auxiliary self-supervised objective. So it's only used during the training of the network and then discarded at inference time. And this auxiliary objective is to take the lane GCN encoded features and predict simultaneous non-factorized joint predictions and just supervise it with a regression loss. And why would we do this? Well, these features are going to be used downstream to reason about the multi-agent future interactions. So we would like the features to have some information about the future. And so we would like them to be future aware. In other words, we want them to be predictive of the future. So now that we have these future-aware lane GCN encoded features, we can now predict this interaction graph that we're going to use for factorized decoding. And so this part of the network is the directed acyclic interaction graph predictor, which is going to predict this interaction graph. And really, this prediction task is just set up as a multi-class classification problem over the edges of a fully connected, undirected graph, where the nodes represent agents. And so we just use a graph neural network to facilitate this prediction. But to be able to supervise this task, we need labels. So we're going to derive heuristic labels on the edges of this graph. And this classification problem has three labels. So if we were to look at green and blue here, there's three possibilities. Either green and blue are not interacting, so that's the no interaction label. Or green influences blue in the interaction, so that's green influences blue, or the other way around, blue influences green. And so to derive the interaction labels, we take inspiration from the concept of conflict areas. By which I mean that if two agents in their future are going to occupy some shared space, so there is a conflict area, then we say they are interacting. And whoever reaches the conflict area first is determined to be the influencer. The other agent is the reactor. So if we were to take this scenario as an example, since red merges in front of the blue vehicle and occupies that shared space in front of the blue vehicle first, then red is going to be the influencer, blue is the reactor. So in the interaction graph, there's going to be an edge from red to blue. And once we have these interaction labels, then we can predict the interaction graph and supervise it just with gradient descent. And here we use a focal loss because the interaction labels are very imbalanced. And then we can threshold the softmax scores output by the predictor to attain a discrete predicted interaction graph. And then we need to make it acyclic. So we perform this additional procedure called DAGnification, which iteratively removes all the cycles in the graph just by enumerating them using an algorithm called Johnson's algorithm. And so at the end, we will have a discrete directed acyclic interaction graph. So with the future-aware lane GCN encoded features and a discrete directed acyclic interaction graph, we can now perform this factorized joint decoding. And I've explained at a high level previously how this works, so we'll look at it in more detail. So we are omitting the red agent on the bottom just for ease of explanation here. So we're first going to produce associated marginal predictions for the source nodes. So that's for the green and orange agents. And then we encode the futures with an MLP as shown by this blue block. And then now, if we want to predict the future of the blue agent, we are first going to aggregate the information about the encoded predicted futures from its parents, and we do this via graph attention. And then the feature vector that is derived from graph attention is going to be fused into blue's feature representation using a GRU. And so really this graph attention plus GRU process is just fusing the conditional context about the predicted future of the parents in the DAG into blue's future feature representation so that we can facilitate conditional prediction. And one additional technicality is, remember that we want to predict not only one future, but k futures. So k equals 2 is shown in this diagram here. And to predict k futures, what we do is we concatenate a one-hot encoding of the modality index before trajectory decoding, which is shown here. So we have 1, 0 concatenated to this set, this modality set, and then 0, 1 concatenated to the second modality set. And then to ensure that the k futures are diverse, we use what's called a winner-takes-all loss, which means we're only going to backpropagate the loss computed on the best of the k predictions. And then we can just supervise this decoder with your standard L2 regression loss and train it via gradient descent. Okay, so that is FJMP. Let's now look at how we train this system. So we train FJMP in 2 stages. The first stage is shown on the left, and in the first stage, all we're going to train is this interaction graph predictor. We also have this auxiliary proposal decoder header. It's the self-supervised objective, and then we train it to convergence. We then freeze the weights of the interaction graph predictor and train the second stage, where in the second stage, we are training the factorized joint decoder, also with another auxiliary proposal decoder header. And then at inference time, we discard all the proposal decoders, and we just train, use the interaction graph predictor and the trained factorized joint decoder. All right, so that's FJMP. Let's now look at how FJMP performs on the interaction multi-agent test set. So this is the, at the time of publication, was the only existing public benchmark for multi-agent joint prediction. And so on the left, we have the competing methods, and on the bottom, we have our proposed method, FJMP. And we are evaluating the commonly used motion prediction metrics, such as min ADE or minimum average displacement error, which is the average displacement error computed between the best of k joint predictions and the ground truth. Min FDE or minimum final displacement error, which is just the displacement error at the final endpoint between the best of k joint predictions and the ground truth. Seen miss rate, or SMR, is just the proportion of agents that miss the ground truth trajectory, where a miss is defined as a final displacement error of at least 2 meters. Cross-call or cross-collision, this just measures the proportion of modalities that contain at least one collision. And then CMR, or consistent miss rate, is the exact same as seen miss rate, but if your seen prediction contains a collision, we count this as a miss as well. And this is the official ranking metric on the right. And what we can see is that FJMP outperforms the existing methods in minimum, average, and final displacement error as well as the ranking metric. So it ranks first on this benchmark. And all of these competing methods are non-factorized, which demonstrates the benefit of factorization. But to directly assess the benefit of factorization, we perform an ablation study. So we compare FJMP against a baseline, which we call non-factorized, which is exactly the same as FJMP, so the same feature encoder, same training hyperparameters. But instead of doing the factorized decoding, we just do the simultaneous decoding. And what we can see is that the displacement error metrics consistently improve with the factorization, most significantly on the interactive metrics. So on the right here, we have the interactive min FTE and ADE, where we are only computing the displacement errors over the agents that are interactive. So they have an incident edge in the ground truth interaction graph. So for example, we can see that on Argoverse 2, we get a 3 centimeter improvement in the overall displacement error, final displacement error, but close to a 10 centimeter improvement when just looking at the interactive agents. And now for some qualitative results. So here we have an example of a left turn scenario where FJMP better handles the interaction between the left turning vehicle and the vehicles going through the intersection. So in yellow, we have the ground truth past, green, we have the ground truth future, and red is the best prediction for each method. And we can see that FJMP captures this left turn mode, whereas the baseline misses it. And then we can see also in the predicted DAG that we have this, this influence of 1 on 0. Additionally, we have another scenario where FJMP better captures the leader-follower interactive behavior. So here we have that FJMP correctly predicts that 0 and 1 are going to be following each other and turn right. And this is also reflected in the predicted DAG. But the baseline erroneously predicts that the vehicle is going to go straight through the intersection. So just some takeaways with FJMP. So what did we propose? We proposed a novel joint motion prediction framework, FJMP, which exploits this idea of factorization. And we show that FJMP is a performant joint predictor that outperforms existing non-factorized methods across multiple autonomous driving datasets. And we also showed in the ablation study that the benefit of FJMP can be directly attributed to this idea of factorization, and we get most of the improvement in the interactive agents, which is expected. And finally, FJMP is also more interpretable than existing methods, because FJMP doesn't only produce joint predictions, it also produces this interaction graph, which is the model's prediction of how the agents are going to interact with each other in the future. And so we can interpret and scrutinize this graph both during training and inference time. And we were doing exactly this when looking at the qualitative results. Another benefit is that since the decoder conditions on the interaction graph, at inference time, we can modify or intervene on the interaction graph to produce counterfactual predictions. So for example, we could say, well, what if this edge was removed? Or what if this edge label was flipped? And then we can see the downstream predictions and what FJMP would produce as a result of that. And here I'm going to discuss some limitations and some future work that we're currently working on in the WISE lab with FJMP, mostly motivated by the current limitations of FJMP. The most important one being that FJMP only predicts one interaction graph. But given a past, there are multiple ways that the scene could evolve in the future, and so there's multiple possible interactions. And so, for example, what if the blue agent was actually an aggressive driver and he refused to let red in? Well, in that case, there wouldn't be an edge from red to blue, but it would be flipped. There would be an edge from blue to red. And so instead of just predicting one interaction graph, we are instead working on predicting a distribution of possible interaction graphs, and we can sample from this distribution to condition on multiple interaction graphs during decoding. And finally, prediction is not really complete without planning. And so we would really like to see how FJMP performs when it's integrated with a planner to truly assess the value of factorization for downstream planning. Thank you. I will conclude here. Thanks.